Alright, so we're going to start the last section of relativity, and we're going to basically start general relativity. So one of the things that one of the reasons why special relativity exists is because Einstein really didn't have the math and couldn't do the math for a more general version that dealt with accelerations. And so he could only do with inertial frames where the math was simpler, and we got special relativity. And I think it took him something like 15 years after special relativity to generalize it to do a general relativity that included non-inertial frames. So that's essentially what this is. This is like the more complete theory of things. Special relativity is a special case, only inertial frames type things, but this is general and includes covering all frames. And you'll find that as we do this, we will encounter a lot of the same sort of things. There'll be a time dilation for non-inertial frames and things like that. One of the big things that comes out of general relativity is, and we've talked in the past about how inertial mass, the one that tells you how much inertia an object has, is related to gravitational mass, that they were somehow related, and everybody kind of thought this and no one knew right. And Einstein came along and said they're not just related, it's not just that they're similar, they are the same thing and they have to be the same thing. And this came from something called the equivalence principle. The equivalence principle. And this was the real foundation for general relativity in dealing with inertial frames. So the idea is, if you were in a rocket, right, in a rocket, no windows, you can't see out of it, okay, and this rocket was accelerating, a bunch of fire coming out of it, right, boosters going, and it was accelerating at a rate of 9.8 meters per second squared, and then you were standing inside here. There's no windows or anything. You can't look out and see anything. You can't hear the engines. They're real quiet and everything like that. Would you be able to tell the difference between this situation? Is there any experiment you could do inside this rocket that would tell you that you were in a rocket accelerating rather than just sitting on the surface of a planet where your rocket was just sitting here, like on Earth, okay, and you were just standing here on Earth, no windows, no nothing? Would you be able to tell the difference between these two situations? Is there anything you could do to figure out the difference between this acceleration of your rocket and this downward force of gravity pulling you down at g? And ultimately, if you think about it and spend enough time, your answer should be basically no. There's nothing that anyone could do to figure out which situation this was. It's called the equivalence principle. It's the idea that there is no way to tell the difference between gravity and acceleration. Another example is if, let's say you were on a train, and we'll draw the end of the train. So this train is driving away from you, right? Here's the wheels, and so the track's down here, okay? And the train is driving like into the board, right? So the velocity is like the old x. It's going that way. This is the back of the train. Well, would you be able to tell if, let's say this was a perfectly smooth track, right? No bumps or anything like that, and you didn't have any windows, how could you tell if you were moving? Let's say, for example, you're driving along, you can't tell, you can't feel any bumps or anything like that, but let's say suddenly you start to lean to the left side of the, so you're standing in here, you start to lean to the left side of the train, right? You start leaning left. And you think, oh, that tells me I'm moving because if I'm leaning left, that means the train must be turning to the right. And so if we had an above ground view of this same thing, it would be the train tracks curving off to the right. It would make you lean to the left, right? So you're leaning left. This is making you lean to the left because it's turning to the right. Well, let me ask you a question. Would you be able to tell if it was the train turning to the right like that, or if someone just lifted up the right side of the train? Would you be able to tell a difference between those two situations? And the answer is essentially no. It's another version of this kind of thing, that the force of gravity pulling you to the left because the right side of the train was picked up is indistinguishable from the acceleration as you curve to the right of you trying to then go to the left, so an opposite direction acceleration. These are all equivalent situations, and you can't tell the difference. Now, there are situations where you actually could tell the difference, and this mostly comes in from tidal forces. So let's say you were huge. You were like Million Mile Man. So here's Earth, and here you are, you're up here, you're gigantic. Okay? Well, if you're gigantic, then you should be able to notice that your feet are closer to Earth than your head is. That means that a force acting on your feet is actually greater than the force acting on your head. And this would cause you to want to stretch out, right? You'd want to stretch out. Now, if you have your arms, because your feet are getting pulled more than your head, so it's going to pull your feet down more. So it kind of want to stretch you. Well, now let's take a look at your arms. Let's pretend your arms span 1,000,000 miles across. Well, again, there, if you look at the force of gravity, it pulls you towards the center of the planet. So this force line is pointed towards the center, but this force line is pointed towards the center too. And you notice these are not parallel. This essentially gives a net force. If we look at if you break these forces into components, right? It makes like a little triangle, that there is an inward component to the force. And this would be a force that was like basically trying to squish you, to compress you, squishes you from the left and right and stretches you head to toe. All right? And these are called tidal forces. It's where the force of gravity from a planet is different than that. And if you're a Million Mile Man like this, there is no single acceleration that we could give you that would account for this. Now, a couple of explanations for this one are, I've heard it said that this tidal forces is actually where gravity is, and so it's a little outside the equivalence principle. And the other argument is that this equivalence principle does not apply to this situation because the equivalence principle only applies to one single object. And if we look down at this person, you're actually a system of a bunch of different objects all hooked together, a bunch of little atoms and particles, and for each individual particle, the equivalence principle holds 100%. For the person as a whole, when all the objects are talking to each other, the equivalence principle only holds over small scales and over short periods of time. Because you can imagine that if this was what was going on, then if you got far enough away from the planet or something like that, like under free fall or something, which we'll talk about in a little bit, then there becomes a difference then through time. Another little a little better example of this is if you imagine here's a planet and there are objects over here and objects over here and objects over here, and they're all falling toward the center of the planet. Well, what's going to happen as they fall is this distance separating them is going to get closer and closer together. As they get down here, they're a lot closer together than they were here, and that's that kind of inward pushing force where they would be forced closer together, and that same sort of thing is happening on the individual objects here. So the equivalence principle is okay for each of these individual objects, but if they somehow talk to each other, then it's no longer that situation. There's no single acceleration that can replace the gravitational force on all of these. So basically, general relativity doesn't apply to this situation. You can't look at this guy and look at this guy over here and count them together. You have to come over here and solve problems here for him and then transfer around to his relativity depth and solve problems for him. Because the equivalence principle doesn't work over large scales of multiple objects and things like that. It only works on small scales and small things. Okay? If we are looking at this here and we're saying that, going back to this equivalence principle, right, now that I've explained the tidal forces, acceleration and gravity are the same thing. So what general relativity would say is that while you're sitting here on this planet, while you're on the planet, this is actually an accelerated reference frame. So you're sitting here watching this video right now, and you think you're sitting still, but you're actually being accelerated right now. It is the equivalent situation to this one. So technically, you're in an accelerated, non-inertial frame right now. The only time you are not in an non-inertial frame is if, let's say, here's the ground and you're in a room or something and the room is under free fall. Well, what would happen? The room's going to accelerate down at 9.8 and you're going to accelerate down at 9.8, right, this g, and you're going to accelerate together. That means if there's no force between you and the floor. And this is actually the moment right here is if we stop thinking about this as you accelerating downward and we more think of it as at this moment there's nothing pulling you on. So like if you were standing on a scale in this spaceship, it would read your weight, but here if you were standing on a scale, it'd read 0. That essentially this acceleration downward isn't really an acceleration downward, this free fall, right? It's really this free fall is really, this is the inertial frame. This free fall where you think you're accelerating, this is the inertial frame now. Because this is the point where you don't have any gravity acting on you. If you want to think of it a different way, essentially think of it this way. Your acceleration downward, g, is exactly canceling out with the force of gravity that would be pushing you up here. Because remember this here, while you're standing on the ground, the normal force, remember that normal force is pushing you up at the amount equal to your weight, mg, right? Well, here, the force of gravity, like the floor is pushing you up, and it's canceling out with this acceleration downward, and they exactly cancel out. And it's another example of if you're in free fall, you feel weightless. It's because that acceleration can exactly cancel out this force of gravity. So it's another little argument of the equivalence principle. And that weird feeling you get when you fall, like if you go on a roller coaster or you're on one of those Tower of Terror things that just drops you, that weird feeling you get in your stomach is actually the feeling of not being accelerated. It's because gravity and gravity is being canceled out by your downward acceleration, and you're essentially inertial at that point. It's like that net force is 0 almost on you, right? The net force is 0, and you're in that inertial frame, and the two accelerations that are pointed in opposite directions, the gravity down and your acceleration up, they're canceling each other out at this point. Okay, so you've got to start thinking of free fall as the inertial frame, and gravity standing on the surface of the planet is actually the accelerated reference frame. Okay, just more part of the equivalence principle that an acceleration can exactly cancel out gravity if you have an equal acceleration, and then you feel weightless. The next thing this goes with is that if we have in a spaceship like this where we are accelerating upwards, what would that do to light? So let's come down a little bit, and let's say you're in a rocket. Again, that same rocket, and your rocket is accelerating near the speed of light. So this acceleration near the speed of light. Not the speed of light, but near it, because we've already talked you can't do that. Well, if you're standing in here, and you're standing right here, and this time let's say you have a window in the rocket ship, and a beam of light comes in through the window, right? So this beam of light that's shining straight into this window, what's it going to do for you? Now you have to remember, when the light first comes in, it's going here, and you have a certain speed. But as the light continues to move, your velocity perpendicular to it is increasing because you're accelerating, right? You're accelerating. So what happens is the next time, so it travels this little distance and you don't move very much up. But in the next moment, it travels that little same distance. You have moved up some. But then you're going even faster. So the next moment that it travels that same distance, you've actually traveled forward even further and further and further. And what ultimately happens is you would see this light ray bend down and curve. And it would curve down. Okay? I mean, you think about it, your spaceship's here. The next moment the spaceship's moved up a little bit. The next moment it's moved up a little bit even more. So the first time t goes by, you move up an inch. The next time t that goes by, you move up, 2 inches, and then 4 inches, and then 8 inches, and you keep accelerating upward. And that would cause, if you were watching this beam of light come in, it would appear to curve down. And the idea that it came up with was that gravity actually affects light. And since light has no mass, the ultimate conclusion was drawn, though, was that gravity is not a force anymore, but it's a curvature of space and time. Because light is always going to want to travel the shortest distance between 2 points. It's going to want to go in a straight line. And in this accelerated reference here, which is equivalent to gravity, remember this acceleration is equivalent to gravity, that if it accelerates, if this light bends in an acceleration frame, it must also bend in a gravity frame. And if light always travels in straight lines, then that means that the straight lines must be curved, that space itself must actually curve when gravity is present. And this takes us out of that old flat Minkowski spacetime and takes us into what are called curved spacetimes. And from this idea, this prediction, he used this and helped work this out. He actually predicted how much gravity would cause light to bend, and this was confirmed when there was a solar eclipse. So you had the sun here, and the idea was that if there was a star over here, so let's say it's a little purple star that was behind the sun where we normally couldn't see it because light coming from the sun would just, coming towards us, would just hit the sun. We'll make ourselves Earth. We're Earth over here, right? And we're trying to look at this star on the other side. Well, we wouldn't be able to see it because it would be blocked by the sun. But it turns out, according to what Einstein predicted, that light coming from this star that wouldn't normally come to us would go over this way, but it would get close to the sun and its path would get curved. And it would curve over here while it went near the sun, and it would curve, and we would look out, and the star would appear to be over here. Right? We know that it should be over here, but it'll appear to be in the wrong position. And it turns out that this experiment was done. There was a solar eclipse, and they were able to look next to the star, and they were able to find that the amount that was even predicted by Einstein's theory, that the star would be off by, it was off by that amount within an uncertainty. It was very close within the experimental uncertainty and everything of it, that it did actually cause the light to bend. And there's been a lot more experimental evidences of this since then, something called gravitational lensing. You could imagine that if this was really far away and a small, not very bright object passed in front of this, like a black hole or something like that, that it could bend light around it from both sides and make the object appear in multiple places. And this seems to happen too, where they look and see that there's a spot they know, they look in space and they see 2 or 4 or several stars that are all exactly identical. And the idea is that the star is actually, there's something big and massive between us, and it's curving light on both sides of it, making it appear like there are 2 identical stars just near each other in space. But these stars are absolutely identical because we're seeing the same star behind this massive object, and it's called gravitational lensing. And if you watch a movie like Interstellar, you can see that every time they look inside the wormhole, the black hole, it looks like everything's getting like twisted and bent like a funny mirror that you would look through, and it causes things to look kind of crazy and bent. So this curved space-time is the basic foundation of general relativity, and all the mathematics that go into it is all about solving out the math of these curved spaces. So what exactly is a curved space? Well, a curved space, it kind of sounds like what it is. You would look at something like the walls of a cylinder. If you have a cylinder, right, and you say, let's say you can only live on this outer wall of it, not the top of the one, the outer wall. Well, is this a curved or a flat space? Well, you'd think it's curved because the outer wall of a cylinder is curved, but it's actually a flat space. You could take this cylinder or take something flat like a piece of paper, right, a piece of paper, and you can roll that piece of paper up, right? You can roll it up into a cylinder shape, but the paper is flat, so the walls of the cylinder are flat. But now think of something like a sphere. If you've ever seen some of those crazy maps where they take a map of Earth and they flatten it out into a square, and then you have to remember that the stuff on the north and the stuff in the far south, they appear to be much bigger. You know, you look at a map of the United States and Alaska looks like it's almost the same size as the entire continental US, and that's because the surface of a sphere is a curved space. You cannot flatten it out. You can't cut it up and then lay it out perfectly flat. Sometimes they made maps where it was like little slices of a sphere and it looks like this, and they do something like that to try and not cause the map to, be all making the stuff in the north a lot bigger. But you can't flatten out this. This is an actual curved space-time. And a straight line on this curved surface is really just the best you can do. You could imagine if we drew a triangle on this, right, some right triangle, or any triangle, that the angle of all the degrees there would still add up to be 180. It's a flat space. But if you draw a giant triangle on the surface of a sphere, you can actually draw a triangle where every corner is 90 degrees. And 90 and 90, 90, that's definitely more than 180. So you can imagine if this was Earth, you start at the North Pole, you walk down the prime meridian till you hit the equator, and then you turn 90 degrees, and you walk along the equator until you go, I think, like a quarter of the way around the planet. You turn 90 degrees, you walk back north, and you'll end up right where you started, and you'll be perpendicular to it. It'll give you 4 or 3 90-degree angles, and that's the best triangle you can draw in this curved space. And space-time is like that. And it turns out that the way you predict the path that objects take in space-time is they follow what are called geodesics. And geodesics are essentially the straightest line that you could have in a curved space. And a couple ways to think about this. One is, imagine you were in an area, three-dimensional area with a bunch of mountains and hills, and what you did is you took your car, you locked the wheels straight so they couldn't turn, and then you tried to drive. And as you drove through this mountain, you'd follow this curved path, but it would be the straightest path that your car could follow through that curved area that you were trying to go through in the mountains. Well, that's basically what these geodesics are. They are the path that something will follow. So anything in free fall, anything under the influence of gravity, is really going to just follow these curved geodesics of space-time. And things follow the shortest straight line, which is do your fingers, a straight line through space-time is a curved path. And then these geodesics, you have to recalculate them for different objects because they're not a curve through space. They're a curve through space-time, through a space and time. So the geodesic for a beam of light is going to be different than the geodesic for a thrown baseball. Even if they are thrown at the same angle from the same place, the curvature of the light is going to be less than the curvature of the baseball because it's a curve through space and time. So that's these geodesics. And the way you also can calculate these is you go along some curved surface and you do what is called parallel transport. You have some curved surface, so let's say this is the surface of the sphere, and you start right here, and you take your little vector that points straight and you move it to the next little space right next to you, and you redraw it as parallel as you can. So like say it's perpendicular to this curve here, you redraw it. And so as you move along here, you keep parallel transporting. But if you notice, as I do this, the direction keeps changing. And if I were to get here and then start parallel transporting down, so like say this was the surface of a sphere, maybe I can draw this a little smaller. Surface of a sphere, I parallel transport, I parallel transport, I parallel transport. We're like following the curve that we did here for this. I get up here. Now my vector is pointed this way. And so now I parallel transport my vector here, keeping it as parallel as I possibly can along a curve over here, and then I parallel transport it back along, right? So we're doing that same path that I did here, right? This triangle path, okay? And now I take that same parallel transport and I parallel transport it backwards this way, and when I get back to my starting point, I notice that my original vector here is not in the same angle as the vector once I parallel transported around this closed loop. It changed the direction, and so that would tell me that this is a curved space. If I parallel transported along the surface of the wall of a cylinder, if I parallel transported all the way around, like say I did it along this edge, it's here, it's here, and it seems like it's turning, and you're thinking, oh, this is a curved space, right? But as you follow this closed loop and you come back around here, keeping it as parallel as you can, so staying tangent here, then you eventually end up with yourself pointed back in the same direction. This is the flat space. And mathematically, the way you would do this is you just basically take a vector and move it around on a little circular path and see if it's the same vector when you get back to your starting place. And you do that with some derivatives and things like that that allow you to, derivatives move things and change them through. So you do a little derivative, infinitely small little circular path of your vector, and it tells you if your your space is flat. Okay, and our space here is not flat. It's curved with geodesics, and things follow a geodesic path through space-time. Okay, the last thing really about, or not the last thing, but a couple more things. Another example of these kind of geodesics getting things done right is that there is, if you look at a planet, its orbit is an ellipse. Well, planets' ellipses, they don't exactly stay elliptical. What they do is they kind of slightly shift. And so I'm exaggerating it here, but they don't follow exact ellipses. These elliptical paths that they follow, they precess. They slowly change over time. And for the planets in our solar system, it's a very small effect, much smaller than this. They barely move over a long period of time. But for Mercury, it happens a lot. And it was actually measured a long time ago that this happened for Mercury. I think back in the 1800s it was. And this was a failing for Newtonian gravity, because Newtonian gravity couldn't account for why these ellipses would precess and rotate like over time. Well, Einstein actually went through, used his general theory of relativity, and was able to calculate out and predict the precession of Mercury's orbit down well within experimental uncertainty, down within a percent, like real small, a fraction of a percent within what it actually is. And so it was a great triumph too, was that his general relativity predicted this motion for Mercury. It's most pronounced in Mercury, so we see it most in Mercury. But it got the precession of Mercury's orbit correct. Now, one of the things that has to go with relativity is that everything has to be done in tensors. And I think what I'm going to do is give you a little time to think over what I've just talked about in this video. Maybe find a video that talks a little better about it than I have just these pictures here, and put that up for you as well. Yay YouTube. But I want you to think about this a little more, and then the next video we're going to talk about the tensor nature of physics and of general relativity. But this one's getting a little long, so I'm going to go ahead and cut it off. So, all right, that's be about it for now.